Determining the appropriate transformer size for a mixed load involving mechanical equipment, lighting, and receptacles requires careful calculation and consideration of diversity factors. Let's analyze the provided scenario involving a 480/277 volts, 3-phase 4-wire, 2000 amp service entrance feeding 1243 kVA mechanical loads and 400 kVA of lighting and receptacle loads. The utilization voltage for the lighting and receptacles is 120 volts. The 400 kVA load calculation includes 100% of the lighting load, 100% of the equipment loads, the first 10 kVA of receptacle loads, and 50% of the remaining receptacles. The question is whether a 75% diversity factor can be applied to the total connected loads, allowing the selection of a 300 kVA transformer. The initial step is to calculate the apparent power in volt amperes for the 400 kVA load. This is a straightforward conversion using the formula apparent power equals kVA multiplied by 1000. Therefore, 400 kVA multiplied by 1000 equals 400,000 volt amperes. Now let's apply the diversity factor to the total connected load. A diversity factor of 75% or 0.75 indicates that not all loads are expected to operate at their maximum demand simultaneously. The total connected load is 400 kVA. Applying the diversity factor, the reduced load becomes 0.75 multiplied by 400 kVA, which equals 300 kVA. The next critical step involves determining the appropriate kVA rating for the transformer. The reduced load after applying the diversity factor should be less than or equal to the kVA rating of the transformer to ensure the transformer can adequately supply the load without being overloaded. In this case, the reduced load is 300 kVA. Therefore, a 300 kVA transformer is suitable for the 400 kVA load when a 75% diversity factor is applied. It's important to understand the concept of diversity factor. The diversity factor accounts for the fact that not all electrical loads operate at their maximum demand at the same time. This is especially true in mixed-use facilities where lighting, receptacles, and mechanical equipment have different usage patterns. For example, lighting loads might peak during certain hours, while mechanical equipment might cycle on and off based on temperature or operational needs. Receptacle loads also vary depending on the type of equipment plugged in and their usage patterns. By applying a diversity factor, the calculated load is reduced, allowing for a smaller transformer to be used, which can result in cost savings and improved efficiency. However, it is crucial to select an appropriate diversity factor based on a thorough understanding of the load characteristics and usage patterns. Overly aggressive diversity factors can lead to undersized transformers, which can result in voltage drops, overheating, and potential equipment damage. Conversely, overly conservative diversity factors can lead to oversized transformers, which are more expensive and less efficient. Several factors influence the appropriate diversity factor, including the type of loads, the size of the facility, the operating schedule, and historical data on load usage. Consulting with experienced electrical engineers and reviewing relevant industry standards, such as the National Electrical Code, are essential steps in determining the appropriate diversity factor. In the specific scenario presented, the 400 kVA load is comprised of 100% lighting load, 100% equipment loads, the first 10 kVA of receptacle loads, and 50% of the remaining receptacles. This breakdown provides valuable insight into load characteristics. Lighting loads tend to be relatively predictable, especially in modern facilities with energy-efficient lighting controls. Equipment loads can vary depending on the type of equipment and their operating cycles. Receptacle loads are the most variable and unpredictable, as they depend on the type of equipment plugged in and their usage patterns. By separating the receptacle load into two categories, the first 10 kVA and the remaining receptacles, the calculation accounts for the fact that the first few receptacles are more likely to be used for essential equipment, while the remaining receptacles might be used for less critical loads. This approach provides a more accurate estimate of the actual demand. When applying a diversity factor, it is crucial to consider the potential for future load growth. Electrical loads tend to increase over time as facilities expand or new equipment is added. Therefore, it is prudent to include a safety margin in the transformer sizing calculation to accommodate future load growth. A common rule of thumb is to add 25% to the calculated load to account for future expansion. However, the appropriate safety margin depends on the specific circumstances and the expected rate of load growth. In addition to the kVA rating, other factors to consider when selecting a transformer include the voltage rating, the impedance, the cooling method, and the efficiency. The voltage rating must match the supply voltage and the load voltage. The impedance affects the voltage regulation and the fault current. The cooling method depends on the environment and the load requirements. The efficiency affects the operating cost and the environmental impact. Transformers are available in various types, including dry-type transformers, liquid-filled transformers, and solid-state transformers. Dry-type transformers are typically used indoors and are air-cooled. Liquid-filled transformers are typically used outdoors and are oil-cooled. Solid-state transformers are a newer technology that offers improved efficiency and controllability. The selection of the appropriate transformer type depends on the specific application and the budget. The National Electrical Code provides comprehensive guidelines for the installation and maintenance of transformers. NEC Section 450 covers the requirements for transformer overcurrent protection, grounding, and ventilation. Compliance with the NEC is essential to ensure the safety and reliability of the electrical system. Transformer overcurrent protection is critical to prevent damage from overload or short-circuit conditions. The overcurrent protection device, such as a circuit breaker or fuse, must be sized appropriately to protect the transformer without causing nuisance tripping. The NEC specifies the maximum allowable overcurrent protection for different types of transformers. Transformer grounding is essential to provide a low impedance path for fault current to return to the source. This helps to minimize the risk of electric shock and equipment damage. The NEC specifies the grounding requirements for transformers, including the size and type of grounding conductors. Transformer ventilation is necessary to dissipate heat generated by the transformer. The NEC specifies the ventilation requirements for transformers, including the minimum clearances around the transformer and the type of ventilation system required. Regular maintenance is essential to ensure the long-term reliability of transformers. Maintenance tasks include inspecting the transformer for signs of damage, cleaning the transformer, checking the oil level, and testing the insulation resistance. A well-maintained transformer can provide decades of reliable service. In summary, sizing a transformer for mixed loads requires careful calculation and consideration of diversity factors. The key steps include calculating the apparent power, applying the diversity factor, and determining the appropriate kVA rating. It is crucial to select an appropriate diversity factor based on a thorough understanding of the load characteristics and usage patterns. Other factors to consider include the voltage rating, the impedance, the cooling method, and the efficiency. Compliance with the National Electrical Code is essential to ensure the safety and reliability of the electrical system. The calculation process started with determining the total apparent power for the 400 kVA load, converting kVA to volt amperes using the formula apparent power equals kVA times 1000, resulting in 400,000 volt amperes. Then, the diversity factor of 75% was applied to the total connected load to account for the fact that not all loads operate at their maximum demand simultaneously. This reduces the effective load to 300 kVA. Finally, the appropriate kVA rating for the transformer was determined by ensuring that the reduced load after applying the diversity factor was less than or equal to the transformer's kVA rating. Since the reduced load was 300 kVA, a 300 kVA transformer was deemed suitable for the 400 kVA load. It is important to remember that this analysis assumes that the diversity factor is accurately reflecting the actual load profile. A poorly chosen diversity factor can lead to an undersized or oversized transformer, each with its own set of drawbacks. Firstly, an undersized transformer will not be able to handle the load during peak demand, leading to voltage drops, overheating, and potential equipment damage. Secondly, an oversized transformer will be more expensive upfront and less efficient during normal operation. In the context of the specific load composition, where the 400 kVA load is comprised of 100% lighting load, 100% equipment loads, the first 10 kVA of receptacle loads, and 50% of the remaining receptacles, it's helpful to consider each component individually when evaluating the diversity factor. Lighting loads are generally more predictable, particularly with modern lighting systems that incorporate controls such as dimming and occupancy sensors. Equipment loads can be more variable, depending on the types of equipment and their duty cycles. Some equipment may operate continuously, while others may only operate intermittently. Receptacle loads are the most unpredictable, as they depend on the types of devices plugged in and their usage patterns. Dividing the receptacle load into two categories, the first 10 kVA and the remaining receptacles, recognizes that the first few receptacles are likely to be used for essential equipment, while the remaining receptacles may be used for less critical loads. This approach helps to refine the estimate of the actual demand. Additionally, when selecting a transformer, it's essential to consider not only the kVA rating but also other factors such as the voltage rating, impedance, cooling method, and efficiency. The voltage rating must match the supply voltage and the load voltage. The impedance affects voltage regulation and fault current levels. The cooling method, which can be either air-cooled or liquid-cooled, depends on the environment and the load requirements. The efficiency affects operating costs and environmental impact. The National Electrical Code provides comprehensive guidelines for the installation and maintenance of transformers. NEC Section 450 covers requirements for overcurrent protection, grounding, and ventilation. Adhering to the NEC is crucial for ensuring the safety and reliability of the electrical system. Overcurrent protection, typically provided by circuit breakers or fuses, is essential for protecting the transformer from overload and short-circuit conditions. Grounding ensures a low impedance path for fault current to return to the source, minimizing the risk of electric shock and equipment damage. Ventilation is necessary to dissipate heat generated by the transformer. Regular maintenance is also essential for ensuring the long-term reliability of transformers. Maintenance tasks include inspecting for damage, cleaning, checking oil levels, and testing insulation resistance. A well-maintained transformer can provide decades of reliable service. In this specific scenario, applying a 75% diversity factor and selecting a 300 kVA transformer appears to be a reasonable approach, provided that the diversity factor is justified by a thorough understanding of the load characteristics. However, it's crucial to consider potential future load growth and to incorporate a safety margin into the transformer sizing calculation. It's also advisable to consult with experienced electrical engineers to ensure that the transformer selection meets all applicable codes and standards. The NEC provides tables and guidelines for calculating feeder and service loads, including demand factors and diversity factors. These tables are based on extensive research and field data and provide a valuable resource for electrical designers. However, it's important to understand the assumptions and limitations of these tables and to apply them appropriately to the specific application. In some cases, it may be necessary to conduct a load study to gather more detailed data on the actual load profile. A load study involves monitoring the electrical demand over a period of time to identify peak demand and load patterns. This data can then be used to refine the transformer sizing calculation and to ensure that the transformer is adequately sized for the actual load. In conclusion, sizing a transformer for mixed loads is a complex process that requires careful consideration of many factors. By following a systematic approach and consulting with experienced professionals, it's possible to select a transformer that meets the needs of the load while ensuring safety and reliability.